Hello, everybody. I am really disappointed that I'm not there with y'all together in person to do this lesson. We have just been talking about exponential functions, and if you recall, if I look at the parent exponential function, let's say y equal b to the x, if I'm looking at a value of b that is greater than 1, I'm looking at exponential growth. So that's for when b is greater than 1. If I were to reflect that exponential function across the line y equal x, in other words, take the inverse of that exponential function, I'm going to get what is known as a logarithmic function. So I am looking at the inverse of an exponential growth function, in this case, to get the logarithmic function. So what should we be able to recognize? Well, we should be able to see that this point here, that is 0, 1, on, well, any parent exponential growth function, becomes the point in the inverse 1, 0. And so we can look at all of our asymptotes that exist. For example, for our exponential growth function, I know I have a horizontal asymptote at y equals 0. That becomes a vertical asymptote for our corresponding inverse of the function, the logarithmic function. So if we keep this in mind, it's a little bit easier to understand how we're arriving at these logarithmic forms of writing exponential functions. So what is a logarithm? Well, a logarithm just means that you are dealing with an exponent. A logarithmic function being the inverse of an exponential function. So if I want to convert from logarithmic form to exponential form, what we need to keep in mind that if I have log base A of C equals B, I can convert that to exponential form. So this would be logarithmic form. I can convert that to exponential form by taking the base of the logarithm. That's the base. That little subscript is a base. That becomes the base of the exponential form. That is going to equal b in the logarithmic form, and that logarithmic value, log base A of C, which is b, that logarithmic value becomes the exponent of the base A. Now that is going to equal the argument C. So most people find it easier to go from logarithmic to exponential form, but you should be able to go in either direction. So given a logarithmic equation, can we represent it in exponential form? And given an exponential equation, can we represent it in logarithmic form? So if I keep this in mind, if I look at an example, so let's say I have log base 2 of 16 equals 4, I can represent that in exponential form as the base 2 to the 4th power equals 16. So what if you have an exponential equation and you're asked to represent it in logarithmic form? Well, you'd read this as 2 to the power of 3 equals 8. So to convert that, it would be log base 2 of 8 equals 3. Now, if I wanted to do another example in general, I could say, in this case, a to the power of x equals y, so log base a of y equals x. So that's how you would convert from one form to the other. Now, let's go ahead and see how we would be able to evaluate some logarithms. So let's say you are given these logarithmic expressions, and you're being asked to evaluate these logarithmic expressions. Well, you can actually do some of these without a calculator. So let's say I wanted to represent this first logarithmic expression in the form of an exponential equation. Well, I could set this equal to x and then rewrite this logarithmic equation in an exponential form. So that would be 2 to the power of x equals 16. So this is the exponential form. And so that would allow me to say, okay, 2 to what power is 16? Well, 2 to the 4th power is 16. So in this case, log base 2 of 16 equals 4. Now, we're going to learn some rules that allow us to use shortcuts to do this, but this is one way we could do it. So if I look at the next one and I were to rewrite it in exponential form, it would be 7 to what power equals 1 over 49. Well, you would ask yourself, okay, 7 to the 2nd power is 49, so 7 to the negative 2nd power would be 1 over 49 if we remember how to convert and address negative exponents. So in this case, x would equal -2. So this logarithmic expression equals -2. In the next example, if I wanted to write it in exponential form, it would be 25 to what power equals 5? Well, I know if I take the square root of 25, I'm going to get 5. So in this case, x is going to equal 1/2. So this logarithmic expression equals 1/2. Now, last but not least, if I wanted to represent this in exponential form, it would be, well, I could set this equal to x, and I could say 2 to the x power equals what? The 5th root of 2. Now, I could rewrite the right-hand side as 2 to what power? Well, 2 to the 1/5 power. Since the bases are the same, I can just equate the exponents, and I'd get x equals 1/5. So this would just equal 1/5. So that's one way to evaluate logarithmic expressions. Now, there are some basic properties that make working with logarithms much easier. So if I have this equation in exponential form and I wanted to rewrite it in logarithmic form, it would be log base b, which we would get from here, of b, which I would get from here, equals what? The exponent of the left-hand side, which would be 1. So what this is telling you, and what you should be able to recognize, is if the base of the log equals the base of the argument, then that just equals the exponent of the argument, in this case, 1. So if I were to give you log base 5 of 5, you should immediately be able to tell me that that equals 1. Why? Because 5 to the 1st power equals 5. Now, similarly, if I give you log base pi of pi, again, you should be able to tell me that's 1. So if the base of the argument equals the base the base of the logarithm equals the base of the argument. The answer is just the exponent. So if this were a different number, it would be equaling a different number. Similarly, if I have b to the 0 power equals 1 in logarithmic form, I can rewrite that in exponential form. I can rewrite that in logarithmic form as log base. What is the base of the left-hand side? B. What is the argument? 1, the right-hand side here. And what is that going to equal? 0. So this is telling you that b to the 0 power equals 1. Now that actually makes sense, because if I think about the input, the domain value, 1 of a logarithmic function, if we think back to our parent logarithmic function, we said that when the input was 1, the output was 0. So the input to this logarithmic parent function is 1, the output is 0. So if the input to your logarithmic function, and it doesn't matter what the base is, if the input is 1, my apologies, if the input is 1, whatever the base is, the base could be 5,000. If the input is 1, the output is 0. So it doesn't matter what the base of the logarithm is. If the input is 1, the output is 0. Why? Because 5,000 to the 0 power is 1. Pi to the 0 power is 1. Any base, technically other than 0, raised to the 0 power is always 1. Now, how would I go about graphing these logarithmic functions? Well, I could either graph the corresponding inverse exponential function, and then I could just reflect each one of those points over y equal x, interchange the domain and the range values, interchange the x and y values, and I could automatically get the graph of the logarithmic function. So in this case, I have y equals 2 to the x, and I could create a table of values for that. Now, if I think about it, what domain values can I put in here? Well, anything. So I could put in -2 for x, -1 for x, 0, 1, 2. And if I substitute -2 in for x, I'm going to get 1/4. If I substitute in -1 for x, I'm going to get 1/2. If I substitute in 0 for x, I know I'm going to get 1. If I substitute in 1 for x, I'm going to get 2. And if I substitute 2 in for x, I'm going to get 4. So I could graph that parent exponential function. Y equals 2 to the x, I know has these points. So I'm just plotting these points, sketching a little graph. So for my exponential function, I have this graph. Now, if I take every single one of these points and I interchange the x and the y values, interchange my domain and my range, I'm going to get the inverse of that function. The inverse of that function is going to be this. So I can look at the reflection across y equal x. So if I look at the reflection across y equal x, what's going to happen? This point comes here. This point goes where? Here. This point comes here. And I'm just interchanging my x and my y values. So this becomes 1/4 -2. 1/4 -2. 1/2 -1. 1/2 -1. 1, 0. 2, 1. 4, 2. So that is one way you can graph a basic logarithmic function. I can look at the corresponding inverse of that, the exponential function, by doing the conversions. I could graph the exponential function, interchange my domain and range, and then I have the graph of the corresponding logarithmic function. Now, if I keep going, I can talk about how I find the domain of a logarithmic function. And I apologize for the spacing on this. So if I look at a parent function, so a parent logarithmic function, so if I look at the parent, I know, again, you should be able to do a quick sketch. It should look like this, passing through 1, 0. And that goes for any base of the logarithm. So if I look at this, the domain of this function is going to be, well, I know I have a vertical asymptote here on the y-axis, so it has to be greater than 0, but it goes to infinity. If I look at the range of any parent logarithmic function, do I have any restrictions? No, it's all real numbers. Now, there are two important type of logarithms, and they refer to the base. So if I say I am working with what is known as a common logarithm, and if you look on your calculator, you do in fact have a log button. That means that the base of the logarithm is 10. So if I don't see a base written, you should know it to be 10. I don't need to see it. I know it's there. It is known as a common log. Again, a common log is base 10. If you think of money, tenths, hundredths, thousandths place, ones, tens. We live in the world of base 10. So if I were to go and try to evaluate these logarithmic expressions, let's see if I can do them without the use of a calculator. Well, if I set the first one equal to x and represent it in exponential form, it would be 10 to the x equals 100. Well, 10 to what power equals 100? 2. 10 squared is 100. Now, there's a clever little thing that allows you to more easily evaluate this. I could rewrite this as log base 10 of 10 to the second power. Remember, if the base of the logarithm equals the base of the argument, the answer is just the exponent. Quite nice. So if I look at the next one, again, I could hopefully recognize this and know this to equal 1, but if not, I could represent it in exponential form and say, oh, obviously it's 1. Now, what about the next one? I have log base 10 of 1 equals x. Well, what did we say? If the argument, if the input to the logarithmic function is 1, no matter what the base is, our output is 0. You should know that because, again, I could convert this and ask myself, 10 to what power is 1? What about the next one? Hopefully in the next one you recognize that little trick, that property that states if the base of the argument equals the base of the logarithm, the answer is just the exponent. Now if I look at the next one, is there a way to evaluate this without the calculator? Well, I can't represent 90 as 10 to some power. So let me see. Let me rewrite this in exponential form. 10 to the x equals 90. I don't see a way to simplify this expression and figure out the value of x in this case without using a calculator. So in the calculator, you're going to put the log button, and then the argument is going to be 90. So go ahead and try that. Take your calculator, hit the little log button, choose the log button, enter the argument of 90. So the log button is all the way to the left column between x squared and a button called ln, kind of to the left of the 7 button on the calculator. So what would that equal approximately? Approximately 1.954. You should be able to get that. Now what about this one? Well, this one allows me to tell you about another beautiful property. If you have a base raised to a logarithmic expression with the same base, the answer is just going to be that argument. So what I'm saying is that if I have a base raised to a logarithm with the same base, the answer is just that argument. That's a beautiful property. That's another beautiful property that you should remember. Keep that in mind. Now, moving on. We talked about common logs being base 10. Well, there's another very special logarithm base, and it is called a natural logarithm. If a common log is known to be base 10, a natural logarithm is going to be base e. E is a number. E is a beautiful Euler number. So if you notice, we did some experiments, some explorations where we had to use the base e, and we approximated e. So if you were to see a logarithm with base e, you need to know that that is a natural logarithm. Now there's a shorthand version, a shorthand way of representing a natural logarithm. I can take this log base e and I can rewrite that as ln. The argument stays the same, but an abbreviation for writing a natural log base e, is ln. It stands for log naturel. So that is just telling you that you have a natural log, that you have a log base e. So if I were to ask you what would log base e of 90 be, you would then select the ln button on your calculator because that's a very important type of logarithm. So that's right underneath the log button. And then you would enter in the argument of 90, and what you should be able to get is approximately 4.5. So what if I were to give you log base e of e, which could be represented as ln of e? Well, in this case, hopefully you notice this, and you can rewrite this as just 1. Now, we've talked about graphing parent functions and applying transformations to them. So what happens if I give you y equal, or I should say, well, yeah, let's go ahead and do y. Y equals 3 to the x. That's a beautiful parent function. The corresponding logarithmic function, if I were to take the inverse of this, well, I could have y equal log base 3 of x. And I'll go ahead and put the argument input in parentheses. So I could come up with a table of values, and I could graph each of these. I'll do a quick little sketch. So in this case, I know it passes through 1, 0. It's going to look like this. These are just quick sketches. I would have to make a table of values to be accurate. If I wanted to reflect that across y equal x, I would get the corresponding logarithmic function that looks a little something like this. And again, to be accurate, I would make a table of values for each, perhaps start with a table of values for your exponential function, and then interchange the domain and range to get your logarithmic function. But these are quick sketches, because what I want to talk about is what happens when we apply transformations to this. Well, if I first discuss the domain of this original parent function, exponential function, the domain would be, for this parent exponential function, domain would be all real numbers. The range would be 0 to infinity. The horizontal asymptote would be at y equal 0. Now let's look at the inverse of that, this logarithmic function. For that, the domain would be, well, remember, it corresponds to the range of the inverse. So the domain would be 0 to infinity, because we would have a vertical asymptote at x equals 0. And then the range of this logarithmic function, well, that should correspond to the domain of the exponential function. It would be all real numbers. Now, what happens if I apply a transformation? If I look at the transformation in the exponential equation, so let's say I do y equals 3 to the x plus 1, how does this positive 1 change the parent exponential function? Well, hopefully you recognize that that is a shift, a vertical shift up 1. So now I have this new function looking like this. So what has happened to the horizontal asymptote? Well, if the parent function had a horizontal asymptote at y equals 0, it has been shifted up, so now I have a horizontal asymptote at y equal 1. What is the domain of this shifted? Well, exponential function is still all real numbers. What is the range? The range is now 1 to infinity, because everything's been shifted up. So how is this going to be reflected in the logarithmic function? Well, in the corresponding logarithmic function, remember, this point moves here. This point is where? Here. So what has happened is, instead of having a vertical shift in the exponential function, it becomes vertical shift up, it becomes a horizontal shift to the right in the logarithmic function. So a vertical shift in the exponential function is reflected as a horizontal shift in the logarithmic function. So then I'm going to have the domain. So how would we represent that? Well, that would be represented by affecting the x value. So the domain of my transformed vertical logarithmic function becomes 1 to infinity. My range is all real numbers, and my vertical asymptote, which was originally the y-axis, is now at x equal 1. So I now have shifted my vertical asymptote. So again, a horizontal shift to the right in one function is a vertical shift down in the logarithmic function. So we have to be able to see the relationship between the transformations. Does that make sense? So if I have, for example, I'm running out of space. What else? Where can I move this? Oh, I can go down here. Yay. So then I have, for example, y equals log of x. That would be your parent. And if I wanted to demonstrate a horizontal shift to the right, again, remember we're affecting the domain value, so this is a horizontal shift right 1. And then if I wanted to represent a vertical shift down 1, this would be a vertical shift down 1. So again, we've seen these transformations before. This is nothing new. We said that you could apply all these types of transformations to many different families of functions, and now you're seeing it. I hope this made sense.